In the last few episodes, we designed a 3D star system in Godot, like in the game Outer Wilds. In this episode, we're going to work on the hardest part so far, the player controller. And we'll see how moving the character around isn't just one problem to be solved, it's several challenges stacked on top of each other. So let's get to it and implement a RigidBody3D controller so we can fly around our toy star system. The first thing we need to think about is the difference between being in zero gravity versus being near a planet. In space, the player will be free to move around in any direction. That means full 6 degrees of freedom control, rotating with yaw, pitch, and roll, while thrusting freely in all 3 axes. But near a planet, the mechanics will need to work a little differently. When near a celestial body, the player will need a local up direction. The player movement will happen relative to the planet's surface. And while all that's happening, the camera still needs to remain stable and intuitive as the world moves and rotates beneath the player's feet. So let's think about this controller in 2 different modes, a space mode and a planetary mode. And we'll look at each one in a few minutes. My earlier experiments using a character body 3D controller were helpful. I learned a lot, but it didn't really solve some of the problems I was running into. Once the planets started rotating, and once gravity changed depending on where the player was, and once the player needed to inherit motion from the planets themselves, we could really use the physics engine to help us out. That's why for this version, we're switching from a character body 3D to a RigidBody3D controller. The movement is no longer just setting a velocity and sliding the character along. Instead, it needs to be handled through the integrate forces method, using the physics state directly. This lets us read collision contacts, apply impulses, adjust velocity, and keep the controller tied into the physics engine instead of fighting against it. A big part of this system came from inspiration and reference work I found while trying to figure out how other people approached these problems. I looked at Zen42's work on YouTube and their code on GitHub, and I also found a really useful breakdown of gravity wells in Outer Wilds from Tweedledee on Reddit. Links will be in the description. Those references helped me out a lot because they made it clear that this kind of controller isn't just a player moving around with point-like gravity. It's really about switching between the frames of reference, using different local rolls depending on where the player is, which is a much bigger idea than just pressing WASD. Before we can even look at the player movement, we need to understand the camera a little more. Because the camera is what gives the player the visual feedback and lets them know which flight mode they're in, we're going to need a clean way to tell when the player moves from one reference frame to the other. In space, the camera needs to feel loose and free along all 3 axes. But on or near a planet, it has to stay stable while also respecting the surface of the planet. That means we'll want to use a camera rig that can handle the pitch, looking up and down, separately from the body, while the body itself handles the yaw and the alignment. And we're going to make the camera rig using this nested set of nodes in the player tree. We'll place the camera into the camera pitch node, which is just another node 3D, and that node will act as our character's head. That gives us a clean split. The body itself will handle the orientation, in other words, which way is considered forward, while the camera pitch node will handle looking up and down, at least while the player is near a planet. We'll need a way to control the camera differently when in space, so there's also a transfer step when leaving or entering a planet zone. That matters because if the player is looking up while on a surface and then exits the planet's influence, we don't want the pitch to suddenly snap away. There are a ton of ways we could do this, but I settled on using Area 3Ds surrounding each planet, and I called them orientation wells. As the player enters the region near a planet, the controller starts behaving like that planet is the local reference frame. It gives the character a sense of belonging to the body they're near, instead of constantly fighting global space coordinates. The code keeps track of which planet is currently active using the Area 3D on-enter and on-exit signals. So when the player enters or leaves the zone, the controller swaps between planetary and space logic, and starts the camera auto-orientation logic. The setOrientationPlanet function is straightforward. It fires when the player moves into a planet's orientation well, and it records which celestial body the player is near. The clearOrientationPlanet function resets the player so they're no longer considered near the planet, and it also stores the current pitch into a transfer pitch variable. We'll use that pitch to gracefully reorient the camera to space mode. The apply transfer pitch function will then ease that pitch back into the body over time. Before we get into the actual movement code, there's one more piece worth pointing out. The physics process function is mostly responsible for updating supporting systems each frame. It refreshes the ground raycast, updates the camera pitch, handles any camera transitions between planetary and space mode, and then clears out the mouse input for the next frame. The ground raycast is going to be especially important later. Right now, it just looks like a simple helper node. But when we get into the planetary movement, we'll use it to solve several edge cases that the contact physics alone doesn't handle very well. The actual movement logic lives somewhere else. Because we're using a RigidBody3D, all of the important physics work happens inside of the integrate forces callback. That's where we determine whether the player is grounded, where we apply gravity and align to planets, and inherit planetary motion, process input, and update velocity. We won't walk through this function from top to bottom in one pass, though. Instead, we're going to keep coming back to different sections of it as we introduce each system, starting with the simpler one, spaceflight. Let's start with space mode because it's the easiest part. In space mode, the controller behaves like a 6 degree of freedom spaceship. Using the body's current orientation, we'll get a forward direction, a right direction, and an up direction. Those vectors become the foundation for everything else the player does while flying. For rotation, the mouse movement will control the yaw and the pitch directly on the rigid body. It won't use the camera rig's pitch controls. And rolling is available too because once we're out in space, there's no reason to pretend the player only exists on a flat plane. The controller applies those rotations directly to the body's basis, then normalizes the result to keep the orientation stable over time. Once the body knows which way it's facing, movement becomes straightforward. We'll query the player input to build a movement vector using the body's forward, right, and up directions. And when thrust is applied, the thrust velocity is added in that direction. That means the player can apply thrust freely along all three axes while rotating independently. So in space, the player really is flying the rigid body around the system like a ship in zero gravity. There's no surface to respect, there's no local up direction to preserve, and no grounding logic to worry about. That makes space mode the easy win, and it gives the player a strong contrast before the controller switches into planetary logic. Because once we get near a planet, most of these assumptions stop being true. So how do we make the same character land on a planet and still feel like the same character? Well, when the player enters a planet's influence, the controller switches into planetary mode. Once the player is inside planetary mode, the first question is simple: which way is up? On a planet, we can no longer treat up as a universal direction. The up direction has to come from the planet itself. The code answers this question by taking the direction from the planet's center to the player's current position. That gives us a vector pointing away from the planet's center, and we'll use that as the local up direction. Everything else can build from that, like the player's body orientation, their movement frame, and the camera behavior, and even the definition of what it means to be standing on the ground. But before we can use the new frame of reference, there's another problem we have to solve. The planet itself is moving. The planet is not static in world space. If you recall back to episode 1, we made the planets out of animatable body 3Ds, so they'll have both a linear and an angular velocity. If the player is standing on a spinning body, the controller can't ignore that motion. The code reads the planet's angular velocity and applies that rotation directly to the player's basis. That means the player inherits the planet's spin before any local movement or alignment is applied. This is one of those places where a simpler controller usually falls apart. If the planet rotates and the player doesn't inherit that rotation, the player feels like they're sliding across the surface even when they aren't moving. So this is a critical step. It makes the player part of the moving world instead of a separate object merely touching it. But inheriting the planet's motion is only half the problem. The controller still needs to figure out how the player should be oriented relative to the planet. So, after we've inherited the planet's rotation, we can start aligning the player to the planet itself. Remember that up direction we calculated earlier? Now we're finally going to use it. The controller compares the body's current up direction against the planet up direction and builds a target orientation from the difference. And we're not just snapping directly to that rotation. Instead, the controller gradually blends toward the direction over time. That's handled with a quaternion and a spherical interpolation between the current basis and the target basis. The result is that the character smoothly settles into the planetary frame instead of instantly snapping into place. That makes the transitions feel more natural. It also helps when moving across curved surfaces where the definition of up is constantly changing. Once the body is aligned, we can finally start steering around the surface. Now that the body is aligned to the planet, we can handle turning the character. Unlike space mode, the yaw, or turning left and right, no longer rotates around the body's current up axis. Instead, the yaw will rotate around the planet's up direction. That means turning left and right follows the curvature of the world beneath the player. Once the orientation is updated, the controller can build a new movement frame. The body's forward and right vectors are projected onto the surface using the slide function. In other words, any upward component is removed, so movement stays aligned to the planet instead of drifting away from it. The result is a forward direction and a right direction that hugs the surface no matter where the player is standing. We'll use those directions later when we actually apply the movement. But before we can move, we need to know whether the player is actually standing on the ground in the first place. To understand the next section, we need to jump back to the top of the integrate forces function. The next problem is figuring out whether the player is actually touching the ground. We'll use two checks. First, we'll use the contact points pulled from the physics engine, and second, the raycast we set up earlier with the groundcast node. The contact logic compares each contact normal against the body's local up direction. If the contact looks like a walkable surface, the player is considered grounded. But contacts alone aren't always reliable. Curved terrain, slopes, edges, and small gaps can create situations where contacts briefly disappear. That's where the ground raycast comes in. If the contact test doesn't find a valid surface, the raycast can still confirm that something is directly below the player. By combining both checks, the controller gets a much more stable grounding result than either method would provide on its own. It might also help us later when we're dealing with steep slopes. Okay, now that we know whether the player is grounded or not, we can return to planetary mode and start dealing with the moving planets. Back in planetary mode, there's another problem to be solved. The planet is both moving along an orbit and spinning on an axis. When the player is standing on a rotating world, the ground beneath them already has a velocity before the player does anything. So treating the player's velocity as purely world space velocity doesn't work very well. Instead, the controller asks the planet for its surface velocity at the player's current position. Then it calculates the player's velocity relative to that moving surface. Standing still doesn't mean having zero world velocity. It means matching the velocity of the surface beneath your feet. Without this step, rotating planets would constantly push and slide the player around. With it, the player naturally inherits the motion of the world they're standing on. Mostly anyway. There's still one more trick needed to make standing still feel truly stable. Once the player is grounded and they're not actively moving, we can assume they're trying to stand still. At that point, the controller enters a stuck-to-surface state. The player's position is converted into the planet's local space and stored using the toLocal function. Then, while the player remains stable, that local position is transformed back into world space every frame using the toGlobal function. That keeps the character attached to a specific point on the moving planet, and prevents tiny amounts of drift from accumulating over time. It also eliminates a lot of the jitter that can appear when standing on moving surfaces. I found this especially useful when testing with simple buildings and structures placed on the planets. These kinds of test terrain can expose controller problems pretty quickly, and standing still on them became much more reliable once the sticking system was in place. Standing still is nice, but eventually we need to move the player. So now we can finally apply the player's input movement while in planetary mode. Earlier, we built a movement vector using the surface-aligned forward and right directions. This is where that movement gets turned into actual velocity. If the player is providing input, the acceleration is applied relative to the planet's frame of reference. And when the player is fully grounded, that acceleration will get a boost. The surface thrust multiplier makes walking feel more responsive than free flight movement, and it counteracts the friction between the player and the planet. At the same time, a surface speed limit prevents the player from accelerating to high speeds while walking on the ground. The resulting velocity is then combined with the planet's surface velocity before being written back to the rigid body. So even while walking, the player continues to inherit the motion of the world beneath them. Finally, there's the jump. When the jump input is triggered, the controller applies an impulse along the planet's up direction, not the world up, the planet up. That keeps jumping consistent no matter where the player is standing on the surface. And with that, we've got a controller that can move freely through space, land on a rotating planet, walk across its surface, and jump back into orbit without changing how the player fundamentally interacts with the world. We can probably improve the camera and the sliding physics, but for now it's working well. The audio logic is simple, but it helps sell the movement. If the player is moving through space or flying, the thrust audio will play. When the player is moving while grounded on a surface, the footsteps will play instead. And when player movement input stops or the player states change, the audio will stop as well. These are small details, but they make the controller feel much more alive. And when you're switching between flying and walking, those cues help reinforce what the player is actually doing. Of course, this prototype isn't finished. There are still plenty of rough edges. Steep slopes can cause problems. The player can occasionally get stuck on them. And surface detection still isn't quite as stable as I'd like. The gravity model also has limitations. Right now, gravity is calculated from a point source at the center of each planet. That works good near the surface, but starts to break down if the player moves deeper inside the celestial body, where a single up direction stops making as much sense, and the increased force of gravity can prevent the player from jumping or even moving. There are also some technical improvements I'd like to make across the project. Very little of the planetary movement logic is cached right now. The controller does a lot of calculations every physics frame. And while performance is still acceptable for this prototype, there's definitely room for optimization as the project grows. The current setup also depends heavily on jolt physics. And some of the larger planets are beginning to accumulate fairly large node hierarchies that probably need to be reorganized into their own scenes before they become a problem. So there's still work to do. But even with those issues, this is starting to feel like the controller I'm imagining. So that's the current RigidBody3D controller. We now have a player that can fly in space, land on moving planets, run around their surfaces, and jump back into orbit, all while keeping the camera stable and preserving a consistent sense of control. For a project that started as a rookie 3D experiment, it's a pretty exciting milestone. There's still a lot I'd like to improve. I want to optimize some of the controller logic, continue improving the planets themselves with better visuals, structures, and points of interest, add stronger player feedback through a proper HUD, and eventually build a dedicated RigidBody controller for the player's ship. I'm also sure there are more physics edge cases waiting to be discovered, because if this project has taught me anything, it's that every solution eventually creates a brand new problem. I'd love to hear your suggestions on where to take this star system and the player controller in upcoming videos, so leave your comments below. Thanks for watching the Pathfinder's Codex, and never stop trying new things.